material over and over. So if we don't get a recording one night, it's okay. So vertical line test, the way it works is you're trying to take a vertical line and drop it anywhere on this graph where it would touch the blue line more than once. If it touches it more than once, then that signifies that you have a repeated X value. It's got the same X value and a different Y value for it. If I draw a vertical line anywhere on this one, each one only touches that blue line in one spot. So this one passes the vertical line test. So it is a function. Okay, so an example of one that might not pass the vertical line test. Sketch yourself again a coordinate plane, y-axis, x-axis, and maybe you have a sideways parabola there. If I drop a vertical line on that, we see, hey, that's the same X value, but it's got two different Y values, one up here in the first quadrant, one down there in the fourth quadrant. So that's a repeated X value. So this would be not a function because it fails the vertical line test. There is a place that I could put a vertical line in and only touch once, but that's the only place, that place down here at what would be the vertex of that. If I can put a vertical line anywhere and it touched twice, then it fails and it's not a function out of there. Okay, so that's what we're looking for when we're talking about deciding if something is a function or not. Okay. Any questions about that point? Pretty easy idea there. Nothing too complicated about that. Just a quick test. All right. Next thing is function notation. Same section. We're talking about functions. It has its own notation. Function notation. F of X. You read that F of X. That's how that's read. F of X. It is the same thing as Y. Okay. It's a more descriptive way of telling what Y is. It says Y when X is a certain number. That's what F of X is. It's notation for specifically a certain X value. So when we're dealing with function notation, we can find function value. Function value means taking a problem that is a function, say, for example, F of X, we'll start with something really easy, 3X plus 5, and they want us to find F of negative 5. Okay. That's the instructions. Find F of negative 5. All that means is find the Y value when X is negative 5. That's all that function notation means. So that means to find F of negative 5, I'm going to plug a negative 5 in for X and work that side out. So that'd be negative 15 plus 5. That'd be negative 10. So F of negative 5 is equal to negative 10. That is the same thing as an ordered pair, negative 5, negative 10. So equate those things together. The function notation like this is the X value, this is the Y value. It's the same thing as an ordered pair, X value, Y value. Nothing different. They're the same. Same idea. So function value, take whatever's in parentheses and plug it in the place of X. So example, F of X. Here's our problem. F of X equals 2X squared minus 3X. And we want to find F of, let's do 3. Find F of 3. Plugging in the number. Function looks a little bit different. It's in function notation, so that tells us it's already a function. We don't have to test whether it is or not. It's already that way. So we don't have to do anything to prove it. So I'm going to take 3 and put it in the place of X. That'd be 2. Order of operations. Remember, please excuse my dear Aunt Sally. parentheses, exponents, multiplication, division, addition, subtraction. So you, parentheses, exponents happen first, and then multiplication, division, whatever order you come in contact with them, addition, subtraction, whatever order left to right they go. So exponent's going to happen first for 3 squared. So 2 times 3 squared would be 9. And then you got, then we can do the multiplication or division that happens in the problem. So that'd be 18 minus 9. Right? And then 9. F of 3 for this one. For 9. With the graphing calculator, you can get it to do that for you. If you wanted to type in 2 parentheses 3 and then parentheses, the squared button's over here on the left column up there. Highlighting it up and see it kind of shining in red there. 3 squared minus 3 parentheses 3. You could do it that way and it'll crank out the answer. You could also store a number as X if you wanted to. So like 9, or excuse me, we're putting in 3. So 3, and then there's this button called STO right to the left of the 1. And then you tell it where you want to store that. I want to store it as X. So I hit the button right beside the alpha button. You have a you've got a TI Inspire. Yeah, it's totally different. No, an 84 is what you need. Now, sometimes you can get an 84 faceplate for an Inspire, and I don't. You'd have to order it online to do that. Yeah, I've seen them before, but a TI 84 faceplate, and some, but the back of that thing's got like a switch on it. Yeah, see, this one's going to be completely different. I'm not using this one completely different. This one. I've got an older one that was given to me that I never used of an Inspire. And it's got a switch on the back that you pop, and the faceplate comes off. Or I'll take the Inspire one off and get an 84. Yeah, see if you can find somebody that's got an 84 that you can borrow for the semester and get you through that. So I'm going to store that as X, and then I can type in the problem 2 and then X squared minus 3X, and it remembers, hey, you put a 3 in there in the place of X, so X means 3, and just do it that way. I generally don't use the store function very much at all. I just do the regular calculator stuff with it. Now, the next problem, let's do the same function. So the same 2x squared minus 3x. F of x is equal to 2x squared minus 3x. And let's find 2x inside. We're plugging in a variable expression in there instead of just a plain number. And this is where the calculator doesn't help you so much on this part as it did on the last one. So it's straight up algebra is what we're doing here. So f of 2x, that just means whatever's in here, we're putting in for x. That's all that the function notation means. So I'm going to put a 2x in the place of x. And I'm going to do the same order of operations that I've done. It's just going to have an x left in there. So when I square something, it means multiply it times itself. So 2x times 2x would be 4x squared. And then we'll multiply that by 2. And this is going to be minus 6x. So that's going to be 8x squared minus 6x. And that's all you can do. So it actually ends up being kind of shorter out of that. You don't get a nice answer. And we can't combine these because this is x squared and that's plain x. They're not like terms. You got to have the same letter and same exponent on those letters to be like terms. So those can't be put together. So just leave it just like that. And that's the function notation for that. Sometimes they ask you to plug in a negative x, and this will come up here in a little while. Let's say we had f of negative x. We're using the same, let's use that same function, f of x equals 2x squared minus 3x. And we want to find f of negative x. This comes up later. It's a test that we use for some things. So when we plug that in, it'll be it's like negative 1x. So it's almost the same thing. So what you want, when you see that negative x, you think negative 1x that you're putting in there. So when you square negative 1x times negative 1x, negative 1 times negative 1 turns into positive 1. And then x squared. So it'd be 2 times x squared. And then this one's going to be negative 3 times negative 1 becomes positive 3x. That's just going to be 2x squared plus 3x. That's what that plugged in works out to be. So it's just taking a function and plugging in whatever they put in there. If they put a picture of a tractor in there, you're putting a tractor in place of x. It's just, that's what it means. And then you work it out if possible, if there's anything that can be worked out with that. Do one more like that, and then we'll move on. Let's do one that's a little bit more difficult, just so that we said we did one that was hard. Let's find f of x plus 2. A little bit more math involved here. So we're going to take x plus 2, and everywhere there's an x, put x plus 2. When I square x plus 2, that means take x plus 2 times x plus 2. The most common mistake is for folks to square the x and square the 2 and be done. That's not completely correct with that part. You've got to multiply it out. Distributive property says you multiply x times x, it's x squared. X times 2 is 2x. Then you multiply, distribute this 2. So 2 times x is another 2x. 2 times 2 is 4. I've still got the minus 3x and minus 6 from where I distributed the 3. Okay? So I've distributed x to x plus 2, and then I distributed 2 to x plus 2. And that's how I got this. X squared is x times x. X times 2 is 2x. 2 times x is 2x. 2 times 2 is 4. You get all of those pieces from squaring x plus 2. And then I can simplify that a little bit. 2x and 2x, they're like terms, so that'd be plus 4x. Still got the minus 3x and minus 6. And then I can distribute the 2 to that. That's 2x squared plus 8x plus 8 minus 3x minus 6. Now I can finally finish it up by putting the like things together. So 2x squared, there's nobody else that has an x squared, so there's nobody like him. So he's just going to come down. 8x and minus 3x would be how much? 5x, that's right. And then positive 8 and negative 6 would be positive 2. And there we have finally finished that problem. We're taking a value and finding the function value. Sometimes you've got to find the function value. I showed you with the calculator how to do that. Let's do one with like a decimal in there so we can just practice that. Let's say with the TI-84. So f of x, let's do a different problem. Let's get tired of that other one. 3x squared minus 5x plus 7. That's our problem. think this is example L, yeah. And let's find f of 1.37, something weird like that. Okay, so doing that by hand, not impossible, but not really, doesn't make a whole lot of sense, because we're going to get a decimal answer anyway. So this is what we're doing. So what I'm going to do is I'm just going to type that into the calculator just like that. So I'm typing in 3 parentheses 1.37 close parentheses, and then I'm squaring that, minus 5 parentheses 1.37, what I'm putting in the place of x, close the parentheses, and then plus 7. If I can type it in just like that, it's going to crank out the answer to that. That decimal for that would be 5.7807. There we have that value. So it's just plugging it in with the calculator and working it out there. Works great unless it's one of those like where you had to plug stuff with X in there. The calculator can't do that. And if it can, it's not legal for you to use in here. They make them that do that. They're pretty expensive, but they're pretty neat too. I've seen a few of them. I don't own one. I wish I did sometimes, just because it's neat to watch it do that stuff, but it doesn't really have any. All right, so next, kind of same section. This first section is pretty lengthy as far as how many different things in there, but this is the last thing in this section, okay? And it's about the domain of the function. So functions are the relationship between domain and range. What we focus a lot of the whole course on is the domain of the function. So every different kind of function that we study, when you look at that syllabus, all of the different kinds of functions, we'll talk about higher degree polynomials, rational functions, radicals and logarithms, and all the different kinds that we do. We will talk about domain in every one of them. So this is one of the most important parts of the course, is getting a basis for finding the domain of a function. So the domain of a function. It's the x values, we already knew that, that work, and we'll do work in quotes, for a function. Okay. It's the x values that don't cause issues. When we talk about issues with functions, there's only two things that could go wrong when you talk about a function as far as domain goes. There's only two red flags that would come up. Domain always starts with all real numbers. Okay? In interval notation, we'll talk about different notations, from negative infinity to positive infinity. Thank you, tattoo industry, for bringing back that symbol. People know what it means when you say it now. Or when they see that symbol, they know it's an infinity symbol now. All right, so domain always starts with that. If those red flags don't show up, then all real numbers is the domain. So we're going to talk about those red flags in just a second. But everybody starts with all real numbers. If a red flag comes up, that's when you start trimming some numbers out. Okay? The red flags that can happen. The first one is an X in the denominator. If there's an X in the denominator, what that could be as a problem is you could end up with division by 0. That's why it's a red flag. The only number in the world we can't divide by is a 0. We can divide by negative numbers. We can divide by decimals. We can divide by square roots and all those things, but we cannot divide by 0. That's impossible to do. There's no way you can divide a candy bar into 0 parts. You divide it into 1 part or 2 parts or 4 parts, but you can't divide it into 0 parts. So that's why there's no such thing as division by 0. It's a red flag when we talk about domain. The other red flag that could come up, or does come up, is a square root with a variable inside, and that variable being x. When we're taking square roots and we're talking about domain, and the whole idea of these functions as we deal with them is moving toward putting them on a graph. If it's a square root, we can't take the square root of negative numbers. It has to be positive numbers only. If you remember from a high school algebra class, if you took a square root of a negative number, that's where the little I came in. May have been a while since we've done any of that. We'll see plenty of that in here. But if you took a square root of a negative, that's where the imaginary numbers or the complex number system comes in. So when we're talking about domain and range, we're talking about the real number system, not involving the complex numbers. So when we see an x in the denominator, so that means there has to be a fraction in the problem. If we see a square root with an x inside, so we know what a square root symbol looks like. If those things aren't in the problem, then our domain is going to automatically go to be all real numbers. Always, that's what we're starting with, unless one of these red flags comes up. One of these red flags comes up, we're going to talk about how to fix that, how to get the domain based on which one of those red flags is coming up. So let's look at some examples and try to see red flags showing up and what to do when those red flags show up. Okay, so find the domain. That's the instructions, or state the domain might be the words that they use sometimes. But we're dealing with a function, f of x, and let's start with one, x squared plus 5x minus 7. We look at that one and we see, okay, well, I got an x in there, but I don't see any fractions. So the first red flag can't come up at all. There's not even a fraction in there. I see a squared, but I don't see a square root. So neither of the red flags show up. So that tells me that this one has no red flags. So that's what I'm thinking. I'm thinking no red flags. That means the domain is all real numbers. So the domain, the way you're going to write the domain, we're going to write it in a couple of different notations. The first way is set notation. Set notation, you start with a little curly brace. Can't do it slow. And you put the X, and then this straight up and down bar, and then you write the words all real numbers, and then end it with a little curly brace. The other notation that we use is interval notation. Interval notation is the one that uses the brackets and the parentheses and the infinity symbols and that sort of thing. So domain, if it's all real numbers, then the interval notation for that is negative infinity to positive infinity with parentheses on the outside. What the parentheses means is you can never get to that number and you don't include the end of that little statement there. It looks kind of like an ordered pair, but it's an interval. If you put a square bracket, which is that shape, that means you include that number. So that's like an equal to mark out of that. But you can never have a square bracket on a parenthesis on a infinity symbol, because you never can get there. Once you think you're there, you just add 1, you're not there anymore. So infinity can never have a square bracket. It's always got to have parentheses. As we go through the first chapter, we kind of bounce back and forth between set notation and interval notation. There are times when set notation is useful, and there are times where interval notation is going to be useful. So we're going to use both. So I'm going to try to help you learn to use both. It's not terrible, but having to do both at the same time can sometimes get a little cumbersome for you. But I think it's good to see both, and it helps you learn whichever one you might not be as familiar with. All right, so let's look at this next example. So that's what we're doing. There's just finding the domain. We're not really doing any work on that one. There were no red flags, so there wasn't anything to do. So the next one, here's a function g of x is equal to 5x over x plus 3. So we have a fraction in this problem, and when we have a fraction in the problem, we have to look to see if there's an x in the denominator. And the denominator is the bottom bar of the fraction. So this one, there's a big red flag right there. Got an x in the denominator. So that tells us, hey, can't divide by x. If x were a certain number, then it could get a 0 underneath in the bottom part of the fraction. That'd be division by 0. We can't do that. So what we have to do is set the denominator that has the x in it. So we're going to set x plus 3 equal to 0. When is the denominator going to be 0? That's what we're trying to find. Okay, so we set the denominator equal to 0, and we solve that equation. Subtract 3, x is equal to -3. If x were -3, that would give us 0 on the bottom, and we cannot divide by 0. So that is the restriction on the domain. So the way your domain is going to look in set notation, and this is one of those where I think set notation is easiest. X, straight up and down bar, and then you tell me what x cannot be. X cannot be -3. Okay, that's that same thing we found right there. When we set that equal to 0 and solved it, we were finding what messes this thing up. What's the x value that makes that not work? Okay, what this set notation here says, x such that x is everything except -3. That's what that says. The interval notation for that is a little bit more difficult, but it's also more descriptive. What that means is that set notation said everything except for -3. So what the interval notation does is it tells us everything that's in the domain. It starts at -infinity, and we're cruising along on -infinity all the way towards 0, and we get to -3, and we can't use -3, so we have to skip it. So we put a -3 parentheses, and then we put this U shape right there. It's not the capital letter U, but it looks like it. It's a union. And then we put another parenthesis and -3, and then we cruise on to positive infinity. So what that is it's like a number line. And out here is -infinity. Up here is positive infinity. -3 is somewhere right there. And what's happening is the domain, you're coming this direction, and then -3 is an issue. You've got to jump over it, and you pick up and start right after you get past -3. -3 is the only number that you don't use. You use -3.00000000001. You use that number, and you use -2.9999999, all kinds of nines there. You use that number, but -3 is the one you hop over. So that's what these two domain statements say. Okay? The interval notation tells you everything that's in there. The set notation tells you what's not in there. That's kind of the way you want to think about those. Okay, so we're going to do both of them for the current time on doing this. All right, so let's look at another one. Let's say we had h of x. Example O. H of x, and let's do, maybe we've got the square root of 2x. Let's do -6, plus 6. Okay. Something simple like that. Real simple idea. Remember, the only red flags that can happen are if you got a fraction with an x in the bottom or a square root with an x inside of it. I got a square root with an x inside of it. So that tells me something's going on. Now, what are the only kind of numbers when we talk about domain that we can take the square root of? Back up here. Positive only. So how can we guarantee that 2x minus 6 is positive? Well, 2x minus 6, if we make it greater than or equal to 0, then it's never a negative number, right? So if we set whatever's underneath the square root, we set it greater than or equal to 0 and solve that, that's going to tell us what numbers will keep this thing from giving us a complex number if we take the square root. So I'm going to solve this problem by adding 6. 2x is greater than or equal to 6. Divide by 2. Just simple solving of that. So x has got to be greater than or equal to positive 3. So the domain for this, in set notation, curly brace, x bar, x has got to be greater than or equal to 3. If x is anything that is below 3, doesn't work. We're not going to use it. So x is greater than or equal to 3. In interval notation, what's the lowest number that x can be? Read that inequality. X is greater than or equal to 3. So that means 3 is the lowest number that we can have. Can we use 3? Why? What part of that inequality tells me 3 is okay to use? The equal to symbol. So we're going to use a bracket right there beside the 3. And then it says that all the x's are greater than that. So that means we're going to go toward positive infinity. So there's the interval notation for that. You get the set notation and the interval notation for the domain there. So fraction, set the denominator equal to 0. That's the number you say it's not equal to. Square roots, you're going to set it greater than or equal to 0, and you're going to use that inequality in your domain. Okay, and then build the interval off of that. Okay, let's do a couple more, and then we'll move on to the next section here. Let's say we had f of x is equal to 7x minus 3x squared. I don't know what letter. We want to find the domain or state the domain for that. Okay. Are there any red flags in this one? Don't have any fractions, right? Don't have any square roots. So that means my domain is easy. I don't have to do anything to it. It's x, it's all real numbers. Interval notation, negative infinity to positive infinity. And you don't have to write set and interval beside those. That's just doing that so you help you as you study. So if there are no red flags, you're going to go back to everybody's included, all real numbers out of that. The only time you're not going to have that is if there are some red flags involved. Say we had f of x is equal to square root of 8 minus 2x, and then a plus 7 on the outside. Does that one have any red flags? Yeah, we got a square root in there. So that tells me, hey, I got to do the work that goes along with that. So what do I do for a square root? Yeah, I said 8 minus 2x greater than or equal to 0. Does this 7 that's on the outside have anything to do with it? No, nothing at all. Even if it had an x on it, it would have nothing to do with the domain for this problem, because the part that has the red flag is it carries all the weight, does everything as far as the domain goes. So let's try to solve this one. So what do we do first? You could plus 2x if you wanted to, or minus 8, whichever way you want to do it. Minus 8 works fine too. It doesn't matter. You're going to get the same answer either way. So we have a negative 2x is greater than or equal to negative 8. One more step. Divide by negative 2, right? What is the rule that happens if I divide by a negative when I'm solving inequalities? Y'all remember that? That's right. You got to flip that symbol around. Instead of a greater than or equal to, it becomes a less than or equal to. And then negative 8 divided by negative 2 is positive 4. So anytime you multiply or divide to solve an inequality, you got to flip that symbol around. Okay. So x is less than or equal to 4. So our domain, we're ready to write that out in set notation. All x's as long as x is less than or equal to 4. Set notation is really easy when it's a square root problem, and we like it a lot. But interval notation, not too much more difficult on this one. It says x is less than or equal to 4, so that means we're going to go below 4 for all our answers. So what's the highest number that we're going to use? 4 would be the highest number that we could use, and it's included because we got the equal to mark. And it says everything that's less than that. So that's going to get us down to negative infinity. And we'll use a parenthesis on that. Rewrite that. Negative infinity. So square root, set whatever's underneath the square root greater than or equal to 0. Solve it. That's going to give you your domain for those out of that. What do you do with if it's a fraction? Let's do one more that's a fraction. Let's say k of x is equal to 173 over 3x minus 5 plus 6x plus 87. What part of that matters? The fraction and the x on the bottom. That's the only part of that matters. The 173, the 6x plus 87 doesn't really affect the restrictions on the domain here. It's only this part that's in the bottom there, that 3x minus 5. Well, I need to find out what would make that division by 0. So to do that, I take the 3x minus 5 and set it equal to 0 and get x by itself. So that's going to tell me when x is this, we get division by 0, and that's what I cannot do. So got 3x minus 5. I'm going to add 5 to both sides. We get a fraction on this one, which is absolutely okay. When x is 5 over 3, that's when I got problems. That's the only time I got problems in this particular function. So the domain, again, set notation is obviously easier in most cases. It tells us x cannot be 5 over 3. Not very difficult there. Whatever you get when you solve that, that's what x cannot be. The interval notation, a little bit more difficult when you have a number that you're cutting out. So you're going to start at negative infinity, and you're going to truck along until you get to 5 over 3. And parenthesis, u parenthesis 5 over 3, and then we're going to pick back up and go on to positive infinity. So there's the domain for that particular function in set notation and interval notation. In section 3.1, if you've got the 7th edition, I think it's page 216, but if not, it doesn't matter whatever section 3.1 is, no matter which edition of the book you have, number 15 through 81. I suggest the odds because you got the answers to those in the back. And if you have trouble with one of the odd ones and you want to do one of the even ones next to it, they're usually the same kind of problem. You're more than welcome to email me a problem. I have a lot of students, since I'm only up here one night a week, they will email me, but since we live in the age of technology, take a picture of what you've done and attach that to the email. And that way I can see, hey, you just missed a sign there. You did everything else right, and I can send you back. And a lot of times I'll be, if I'm not by my book and you say I can't figure out number 13, if I'm not by my book, I don't know what number 13 is. So take a picture of it and send it with me. That way, no matter where I'm at, I can usually reply to you and send you something back. And it may be me working it out on a napkin or something and sending you a picture back, but that's what I usually do. So keep that in mind as you're working there. So there's section 1 out of that. So let's move on to section 2. It's not, I don't think it's not nearly as bad. It's not as heavy anyway out of that. So section 2 talks about the graph of a function. All right, so what I'm going to do is I'm going to sketch a graph, and yours doesn't have to be perfect to scale because mine's not. But we're going to take a picture of a graph here, and we're going to answer some questions about it. Straight edge, so mine's a little better organized. So I want to draw an X and a Y axis here. And then we're going to draw some stuff on there. So I'm going to use my lines here for, I'll try to scale it out just right. So my picture looks decent. All right, one more. All right. 1, 2, 3, 4. So I'm going to put a dot right there. That ordered pair is 0, 4. So if you keeping score. Draw a little curved line to that spot. That spot right there is pi over 2, 0. Weird number on purpose. All right, and then I didn't do my scale on the bottom here. 1, 2, 3, 4. All right, so I want to go down to here. Get that dot. That dot is at pi negative 4. We'll draw a little curve to that. We'll curve back up. And that dot right there is at 3 pi over 2, 0. And I'm going to draw a dot right there. Curve back up to there. And that ordered pair is 2 pi 4. And we'll come back down to right there. And that dot is at 5 pi over 2, 0. We'll come down to this spot. Put that at 3 pi negative 4. That's where that dot is. Come back up to there. Guess what? That's it. Everybody's favorite number, 7 pi over 2, 0. And then one more. Oops, went too far. Let me slide that ordered pair out of the way. Rewrite that. Right there is 7 pi over 2, 0. And then right here ending up right there at 4 pi 4. All right, so what we've got here is just a small section of either a sine or a cosine graph. It really doesn't matter out of that. We're not concerned about what function made that graph. We're going to answer some questions about the picture of what's going on here. Okay, so that picture is what we're always going to refer back to as we answer a few questions here. The first question is, what's f of 0? What does that even mean? What's f of 0 looking for? Think back to section 1 about the function notation. What is y when x is 0? So according to this graph, what's y when x is 0? 4. That first ordered pair right there. Right here, x is 0. What's y? It's 4. So the answer to that would be 4. No, that's absolutely fine. If you need to come around, yeah, it's absolutely fine. Yeah, absolutely. Yeah. It's a tough one to do. And I do this one with the different x and y values so that you have to go back and look at it. You don't try to memorize the numbers because it's borderline impossible to memorize all those real quickly. Anyway, some people can. I think my oldest son probably could. He's crazy good at memorizing things in a short amount of time. I don't know how he does it, but he does. Next question, what's the domain of this picture? What does domain even mean? Domain deals with what values? The x values. So what x values are being used by the blue line that's been drawn? The curvy blue line. What's the lowest one? 0. So we start at 0. Are there any gaps as we travel along this blue line? No, there are no gaps. So that means I'm using all of these x values along this blue line here until I get to where and stop. What's the x value right there? 4 pi, right? The y value is 4, but the x value is 4 pi. So that's going to be my domain. So domain, you're looking, if you've got a graph, you're looking at how far does it travel left to right. That's what you want to. You want to read it from the left to the right, just like you'd read a book. Okay, so maybe write that somewhere. Read left to right. Okay. Well, in the same kind of idea, let's state the range. And I'll give you a hint. Read bottom to top. Reason we read bottom to top is because where are our smaller numbers? They're in the bottom part of the graph, right? Just like left to right on the domain, it makes sense to us because we read books left to right, but it's because the lower numbers are to the left and the bigger numbers to the right. So bottom to top. What's the lowest y value? -4. What's the highest y value? +4. Are there any gaps in between those two? The blue line covers all the y values right here between those. Same thing in this little spot and this spot too. There are no empty spots in there. So my range is going to be from -4 to +4. We're reading bottom to top out of that range. So when you look at a graph that asks about range, it's talking about reading it from lowest y value to highest y value. If the differences that could occur, I've got filled in dots on every one of these. They could put undo here. They could put an empty circle somewhere, and that means that number is left out. It's showing up as where it should be, but an empty circle means it's left out. So those things could be where gaps occur. If there are empty circles, that's where a gap occurs. But in our case, there are no gaps in this particular one. Mm-hmm. Yeah. Or either that or there's no blue line there at all. Like it stops here and picks up somewhere else, and there's like empty space in between. So if the line continues, but there's an empty circle in it, you know, hey, there's a spot that it skips in the middle of that. That's how it's going to show up. All right. So next question is name all the intercepts. What kind of intercepts do we have in a math class? You guys remember anything? As far as that goes, intercepts. We could have X-intercepts, we could have Y-intercepts out of that. So X-intercepts are where they're crossing the horizontal axis. Y-intercepts are where it crosses the Y-axis. Okay, so let's get the Y-intercept first. What's the ordered pair for where it's crossing the Y-axis? Y-axis is this one here, up and down. Where's it crossing it? Right there at 0, 4. The Y-intercept is at 0, 4. X-intercepts. This one's a little bit more involved. It's a lot more of those. So that's saying, where is it crossing the X-axis? Well, here's a spot. It's at pi over 2, 0. Here's another one, 3 pi over 2, 0. Here's a third one, 5 pi over 2, 0. And there's a fourth one at 7 pi over 2, 0. So it's at all of those places. Those are all X-intercepts. So pi over 2, 0. 3 pi over 2, 0. 5 pi over 2, 0. And then 7 pi over 2, 0. So all of those ordered pairs are the intercepts for this particular graph. The intercepts, we're looking for X and Y intercepts. It's okay if one doesn't have one or the other. Not every graph has X-intercepts. Not every graph has Y-intercepts. So when you're looking at problems for this, it's not always going to be that way. All right. Next question. Where is f of x, so that's the whole graph, where is it greater than 0? Okay. This is where the interval notation is going to help us. So what does f of x mean again? It's y. So it asks, where's y greater than 0? Okay. So when we look at that graph, where is it greater than 0? Well, here the y value is 4. What do we know about the y value on this part of the blue line right here? What kind of numbers are those? They're somewhere between 0 and 4, right? So they're all positive, right? So it's the graph is greater than 0 from the x value of 0 all the way to pi over 2. So bracket 0, pi over 2. But that's not the only place that it's greater, that the y values are positive or greater than 0. If right here, this part of the graph, it's below the x-axis. So the y values all in this little trough right here are negative. So we know that that's not part of the answer here. This, when it goes above the x-axis, those y values are positive. That starts at 3 pi over 2 and ends at 5 pi over 2. So those are the next, that's the next interval from 3 pi over 2 to 5 pi over 2. The question asks, where's y greater than 0? Where is a location? Locations are generally x values or x intervals. Those are x values that we're reporting. Okay, go back to the graph. There's some more spots. Right here, it again dips below the x-axis, so these are negative values. And right here at 7 pi over 2, it turns into 0 and goes positive again all the way to 4 pi. So there we would have from 7 pi over 2 to 4 pi, and we put a bracket on the 4 pi because it ends right there. It stops. So those intervals there are the intervals for which the graph is positive or greater than 0. All right, so given a graph, being able to inspect it and find certain things like this. I'm going to just ask you a question. The answer's there in the picture. Don't look for them some other place. They're right there in the picture. So be able to look at them. If it says something about domains or location, like where, you're thinking what X values are making this happen. Okay, so be mindful of that. All right. What if there's no graph involved? What if the problem they give us is a function, x plus 1 over x plus 2, and they start asking us questions about it, and we got to find out all this stuff. So the first question they might ask is, state the domain. Well, good thing is we just finished learning how to do that. So how do you state the domain for this particular problem? How do you find that domain? Set what to 0? X plus 2, the denominator of the fraction. You're going to set it equal to 0. So x plus 2 equal to 0 and solve that. So minus 2, minus 2. Domain, all x's as long as x does not equal negative 2. There's the set notation and interval notation. Negative infinity. We're going to get up to negative 2. We'll skip it. And then truck on to positive infinity. Set notation and interval notation for that. I'm just doing both to get the practice, because I'm going to need it later on. Okay. So there are going to be times where set notation is asked for. Sometimes I'm going to ask for interval notation. Being able to do both. Okay. So that's a a question, basic question from earlier in the chapter. So it adds onto that, and then maybe they'll say something like this: oh, where is f of x equal to 2? All right. Well, that's a weird question. Where is y equal to 2? Well, we can find that out because we know, hey, f of x is equal to, this whole equation is f of x. If I take x plus 1 over x plus 2 and set it equal to 2, that's an equation that we should be able to solve. It may look difficult now because it's a big fraction, but if I make it into a fraction equal to a fraction, y'all remember what those are called? Starts with a P, ends with a proportion. You remember doing those? Y'all remember how to do proportions? Cross multiply. You may remember hearing that word. Cross multiply, cross product. So it's bottom times top, bottom times top. So you got 2 times x plus 2, and then 1 times x plus 1. And so that's going to give us 2x plus 4 is equal to 1x plus 1. And now we've got a problem. It's fairly easy to solve. We could subtract x, get x plus 4 is equal to 1, and then subtract 4, and x is equal to negative 3. So negative 3 is where f of x is equal to 2. So the x value is negative 3 for when the y value is 2. Another weird question that could be asked is 1/1/2 on the graph of f of x. What do you mean? You didn't give me a graph. You gave me a problem, not a graph. How can I tell if an ordered pair is on a graph if I don't have a graph? Well, what do I know about that ordered pair? The 1 is what kind of value? It's an x value, and 1/2 is a y value. If it's on the graph, what that means is if I plug in 1 for x into that problem, if I get 1/2 back, it's on the graph. If I get anything else, it's not. 1 plus 1 is 2. 1 plus 2 is 3. This says that for this function, when I plug in 1, I get 2/3, not 1/2. Remember, if it's a function, this x can give me 2 different y values. X's can't repeat. So 1 is either equal to 1/2 or it's equal to 2/3. Well, when I plug it in the math, it's equal to 2/3. So that tells me this is not on the graph. Just doing function value is all I'm doing to do that. It seems like an obscure question, but it's really just a function value question. So the answer to that would be no, it's not on the graph. All right. Last question. What are the intercepts? So again, what kind of intercepts can we have? X and Y intercepts. That's the only kinds we can have. When we talk about intercepts of a function throughout the entire book that we do all this stuff in, X and Y intercepts are what we're going to be talking about. If I say intercepts, I'm talking about either X intercepts or Y intercepts or both. Okay. So to find the intercepts, if I wanted to find the Y-intercept, we started with that earlier, so we'll start with that on this one. How do you find a Y-intercept when you're given an equation? What do we know about Y-intercepts as far as their ordered pairs go? Not the Y. The X has to be 0 because remember on the coordinate plane, any dot that's on this axis has an ordered pair 0 and then some Y value. If it's on the Y-axis, the X value is always 0. So if I plug in 0 for X, I get 1/2. So the Y-intercept's at 0, 1/2. That's one of our intercepts. If I'm looking for X-intercepts, anything that's on the X-axis, the Y value is going to be 0. So to get an X-intercept, we're going to set the whole problem equal to 0. So X plus 1 over X plus 2 equals 0. Well, if I treat that just the same way that I did when I set it equal to 2, and I make that a fraction and cross multiply, what happens when you multiply X plus 2 times 0? You get 0. No matter what you multiply times that 0, you're going to get 0 back. So I get X plus 1 is equal to 0. And that's not too bad to solve. Subtract 1, -1. So the X-intercept is at -1, 0. So we found our intercepts by doing that. So to find a Y-intercept, no matter what the equation looks like, if you're asked to find a Y-intercept, just plug a 0 in for X and work it out. If you're asked to find an X-intercept, you set the whole problem equal to 0. That's all. That's the same rule we'll use almost every chapter that we do, except for the very last chapter. Very last chapter, we don't do all of this stuff. But every chapter other than this, we do a ton of stuff with domain and range and intercepts and all that stuff for different kinds of functions. Okay, so section 2, 3.2. I think it's 224 is the page number. 9 through 47 is the section. Again, I just pick a few of those to do as you're preparing for your Canvas quiz or the exam and things. So whatever version of that book you've got. All right, let's go to the last section of the evening. It's 4:30. We're still going to get out of here early this evening, I believe. And Go from there. So, section 3, properties of functions. Properties of functions. All right, so what we're going to be doing is doing some tests on functions and rules about increasing and decreasing and maximums and minimums of different functions, and then we'll end the day writing some equations of lines that are involved with that. So properties of functions. Functions can be considered odd or even. The odd or even function test. It's the same test for either one. Okay, odd functions and even functions. What you want to do is plug negative x into the function. If f of negative x equals f of x, and when I say that f of x, I'm talking about the original. If you get back everything the same, then the function is even. If f of negative x comes back the opposite, so everybody change signs, then the function is odd. Okay. Let's look at an example. F of x is equal to 6x squared minus 3x to the fourth. Is this odd, even? It could be neither. There's a possibility for that. Okay, odd, even, or neither. There are several odd functions in the world. There are several even functions in the world, and there are a whole bunch of neither functions in the world. Okay, so when we're looking at this, we're just going to plug in that test, and then I'm going to show you a shortcut if you don't realize it already. If I plug in negative x, negative x times negative x would give me positive x squared. So this is 6x squared. This comes back the same. If I take negative x to the fourth power, that's negative x times another negative x times another negative x times a fourth negative x. So these two together would be x squared, and then these two together would be x squared, and then x squared times x squared gives me x to the fourth, and that's exactly the same thing as I started with, right? So this ends up being the exact same as I started with. That is what the first definition is. If f of negative x equals the original problem back, that's what happened here. This is an even function. What I'm saying is anything with an even exponent on it's going to come back the same way as it started. Okay. If all of the exponents on the shortcut is if all of the exponents on the variables are even exponents, then it's an even function. That's the shortcut. If all the functions exponents are even, then the function's even. If all the exponents are even, the function is even. In the same vein, if all the exponents are odd, guess what the function is? Odd. Example of that, negative 8x cubed minus 5x. If I plug in negative x to the problem, negative 8 And that's like negative x to the third power, and then 5 times negative x. So here we have negative x to the third power means negative x times another negative x. So that's going to be negative x times negative x is positive x squared times another negative x will give me a negative x cubed. So that's a negative times negative 8 is going to give me positive 8x to the third. And then when I multiply negative 5 times negative x, I get positive 5x. Notice that is the opposite of what I started with. The original problem had negative 8x cubed. This one has positive 8x cubed. The original had negative 5x. This one has positive 5x. Those are opposites. So this would be an odd function. The shortcut is look at the exponents. Technically, that's a 1 exponent on that plain x that's there. 1 and 3 are both odd numbers, right? So the exponents on the variables are all odd. So that means this is an odd function. Okay, all even exponents, even. All odd exponents, odd. A mix of those would be what? Neither. That's anytime it's mixed up like that, it's going to be a neither. For example, h of x is equal to x squared minus 7x plus 12. If I plug in negative x to that problem, to be even, everything has to come back exactly like it started. To be odd, everything's got to change signs. Is that 12 ever going to change signs? It's never going to change at all. It's going to come back the same. Well, what happens here when I square negative x? I get x squared. I got the same thing back. But what's negative 7 times negative x? It's positive 7x. Is that exactly what I started with? No, that's different. Is it completely the opposite of what I started with? No, this one's not the opposite, and neither is that one. So it doesn't fit either of those bills. It's a mix of even and odd exponents. And then this one doesn't even have an exponent. So this would be a neither problem. Odd, even, and neither. Shortcut, if it's odd, it's got odd exponents. If it's even, it's got even exponents. If it's a mix of any of that, then it's neither. Okay, that's the shortcut. And the shortcut works fine. It doesn't, you don't have to know that test. But math theory and all, that is the test for whether or not something is odd or even. Okay. All right. Once we know that things are odd or even, we get some things about graphs for free. Okay, so by knowing that a function is odd or even, it can help us with a few things with graphs. And these are just rule things. Okay, even functions are symmetric with respect with an S, respect to the y-axis. What that means, symmetric, from high school geometry, symmetric means if you fold it in half on the line of symmetry, then it matches up perfectly. So like if I fold my hands like this, they somewhat match up perfectly, right? So with respect to the y-axis means if it's an even function, that means if I fold the graph on the y-axis, it's going to match up perfectly. So an even function does that. So by knowing it's even, you know it does that, which can help you when you get into some calculus stuff. Not that any of us are getting into the calculus stuff, but definitely not this semester for sure. But if you ever decided to go into that direction, you know, you get a few things involved with that. Odd functions are symmetric with respect to the origin. And the origin is where the x and the y-axis meet up. And the idea of that is that if something is an odd function, you can fold it across the y-axis and then fold it down across the x-axis. That's symmetry about the origin. You fold it both directions, and it would match up after the second fold. That one's tough to see visually without actually taking a piece of paper and folding it. And so when I teach geometry in high school, I actually get some of that. I call it patty paper. It's real thin. It's like wax paper. It's just thinner. And you draw it or trace a picture, and you fold it down and across, and it gets you that symmetry out of that. So even symmetric across the y-axis, you could fold it at the y-axis and it match up. That's an even function. Odd, you could fold it across the y and then again across the x, and it match up. That's odd. So they're visualizing that for graphs out of that based on odd and even functions. Okay, easy peasy. Next. All right, so we're going to talk about increasing, decreasing, and constant intervals. So this is one of those places where the interval notation is going to be useful. Okay, so when we talk about these intervals of increase, intervals of decrease, and constant intervals, we're going to use interval notation out of that. So let's take a sketch here, and this is one of those things where I'm going to draw a graph, and yours doesn't have to be perfect. It's not going to have any gray area to it as far as you're not going to be able to tell something's increasing, decreasing, or constant based on this picture here. It's nothing major out of that. So this point right here is at -6, 0. This point is at -4, -2. This ordered pair right there is at -2, 0. That ordered pair up there is at 0, 4. That ordered pair is at, let's do 5, 4. Okay. I'm going to draw the graph. Use a straight edge here. Make it a little better. That's perfect. Okay. Now, so what we have here is a function of some sort. We don't know the equation for this. Doesn't matter. What we want to do is first state the domain. This goes back to that idea, same as that picture we used in the last section. So what's the domain of this function? -6 and 5. Should that be parentheses or brackets? Brackets. Those are both filled in dots, so they're going to be brackets. Okay. What would be the range? Let's go ahead and get that out of the way, and then we'll get into these intervals of increase, decrease, and constant. -2 up to 4, and we'll put brackets on those as well because they're using those. Okay, now when we talk about intervals of increase, decrease, and constant, we're going to use parentheses on all of those, no brackets, because how do you know where it stops increasing and starts decreasing, or stops being increasing and goes to constant? We can't pick one to be that and justify not picking the other. So we're going to use parentheses all the time when we talk about intervals of increase, decrease, or constant. Okay, so increasing. Let's find the increasing one first. Where is this graph increasing from? As you read it left to right, what does it mean to increase? Go what direction? Up, right? So when I start here and I'm reading it, what's it doing as I go this direction? It's going down. It's decreasing. So that's going to tell me that's probably a decreasing interval. Where does it change directions? At -4, -2, it turns around and starts going up until I get where? To 0, 4. So my interval of increase is from -4 all the way to 0. So I've got an increasing interval from -4 to 0. For this graph, that's the only one. Some graphs may have more than one interval of increase. This one only has one. Okay, so from -4, that's the x value, to the 0 x value for that point up here. It's increasing all the way. We skipped this point, but did it change directions at that point? No, so that's why we just kept going.
Because you don't state the -6 and -4 definition direction. It's not changing. It only changes at -4.
It only changes at -4. That's right. That's right. That's exactly right. All right, so let's do a decreasing, if there is one. I think there is one. We already talked about it a little bit. Where, as we read this graph left to right, where is it decreasing? -6 to -4. So this little leg right here is where it's going down and to the right. So that would be from -6 to -4. It changed directions there and started increasing, and then it changed directions right here, but it didn't start decreasing. That line is flat. So that tells me it's not decreasing. That's going to be a constant interval there. So let's do the constant then. Where does it start being constant, flat? 0 and all the way up to 5, and that's where it stops. 0, 5. And again, we'll just use parentheses there. We stop the graph. We don't know where it goes after that. Graphs can have more than one of any of those intervals. You just got to read it left to right and decide what it's doing. If it's going down and to the right, it's decreasing. If it's going up and to the right, it's increasing. If it's flat, it's constant. Okay, very, very easy idea there. Nothing real fancy about that. It's just reading the graph. Okay, let's talk about maximums and minimums. Local maximum and local minimums. Occur, I'll spell occur correctly, but inside an interval. Sometimes that interval is stated. It tells you look between 6 and 15. Find the local max or local min. Sometimes it's just, okay, here's a snippet of the picture of the function. What's the local max in this picture? What's the local minimum in this picture? So it's the one that occurs locally. It's within a certain window. Okay, when you talk about local, we're talking about within a certain window. Local max would be what? The highest point. Local min would be the lowest point within that certain window. An absolute maximum or minimum occurs across the entire domain. Okay. Local max and min is within a small part of the graph. Absolute is across the entire domain. Okay, so know the differences in those. And again, it's just looking at the graph. Highest point, lowest point. If we're talking about an absolute maximum min, there may not be one. If a graph continues, it has an arrow that points up, and it just keeps pointing, it just goes up, there can't be an absolute max. It's just going to continue going up. So we can't have an absolute max. So not every graph or function is going to have an absolute max or min, okay, depending on what's there. If you had a graph that looked like this, and it did that, That one would have an absolute minimum, but it would not have an absolute maximum because it's got a lowest point down here at the bottom of this little trough, but both of those arrows point up, so it doesn't have an absolute max. We could find local maxes. Right there would be a local max out of that, but it wouldn't be the absolute max. So that's the difference in those two. So just a definition type thing out of that. With the TI-84, you can take an equation and actually find local maxes and mins on there. So let's look at doing that real quick. What letter we're on now? Skipped a few. I didn't write a letter on the last one, so go back up. That was example D with the increasing in interval. There, this will be example E. Not that it matters. Okay. Example E, here's our function. F of x is equal to 3x cubed minus 7x plus 1. All right. And let's first work on graphing that with the calculator. So you got a TI-84 graphing calculator. You're working on that. So here you are. And I'm just at the regular calculator screen, and I want to graph something. So to graph something, I'm going to hit the Y equals button, and I think I can actually put on the key press history here so that you can see. And I'll clear that out so that you can see what's going on. All right, so I'm going to hit Y equals, and I don't have anything in there. If you had an equation in there, you just hit clear, and it'd get rid of it. You just clear out any of them you need. I want to type in the equation that I've got here. So 3 and then the X button. And then to get the third power, I'm going to hit the house top, the caret symbol to the third power. And then I'm going to press the right arrow key to get out of the exponents. And then minus 7x plus 1. Okay. So there's the key press history down there at the bottom. So you can see what I did to get there. And then I'm just going to hit the graph button. And I see a nice pretty graph that shows up there. All right. And I want to find a local max or min. So within this window, a local maximum and a local minimum. So I can tell that there should be a local maximum right there at that point. Okay. My calculator can give me a better estimate than me guessing that that's somewhere around -1 for the X value and somewhere around 1, 2, 3, 4, 5 for the Y value. That would be my guess is that around -1, 5 for the local max. I can get a better estimate of that with my calculator. The way to do that is to hit second trace, and it has a calculate here, and you have the options of a value, a 0, a minimum, a maximum, an intersect, and then those last two are calculus things that you won't use in here. So we're going to use the maximum. So choice number 4. And it asks us, where's the left bound? So what's your interval that you're looking inside of? I'm going to put my interval at -2 because I know that's to the left of where that maximum is. If I put -1.5, that'd still be to the left. I just want to pick something to the left. Okay. And then I'm going to, it says for a right bound, I'm going to pick +2 because that's to the right and it's just a good number in between there. And then it asked me to guess where that maximum is. And what I want to do there is just move my cursor until it gets close to where I thought it was. I thought it was around -1, so I'm going to move my cursor till I get close to -1. That's about as close as I can get right there. And I'm going to hit enter. And it tells me that I have a maximum value at -0.882 and then 5.116. Okay. So local max at -0.882 and 5.116. Okay. I'm going to find the local minimum as well using the calculator. I'm going to do it the same way. Let's clear that out so I'm going to hit second trace, and then a minimum is at 3. So I want a left bound. I'm gonna go to -2, enter, and right bound at +2, enter, because that's the same ones I used on the other one. So that seems like a good spot. Ask me to guess. I'm going to press my arrow and get it down there close to where that is. That's pretty close. We'll hit enter, and it tells me that it's at positive 0.882 and negative 3.116. 882 negative 3.116. So that's using the calculator to estimate where that's at. And again, estimate is going to be get close. Not something that is always done with the calculator there, but it is a way of estimating if you've got an equation and a local max or min. This one would not have an absolute minimum or an absolute maximum because these lines continue forever toward negative infinity down here, and then this line goes up to positive infinity. So there's not an absolute for that particular graph out of that. So local maxes and mins exist, but absolutes don't always exist. They just sometimes do. All right. Last little bit of stuff here from this first evening of fun and excitement in college algebra. All right, so let's talk about average rate of change. You may not have called it this. You may have heard that word before. You may have heard it called slope, because that's what it is. Average rate of change, any kind of rate of change is a slope. Okay, when we talk about it, if you look it up in a collegiate textbook, college level textbook, they're going to use fancy notation, delta y over delta x, and then they'll use f of b minus f of a over b minus a, and it looks like it's super complicated, but when we were in high school, we learned it this way: y2 minus y1 over x2 minus x1. You may have that may be more familiar to you. That m was what we called slope. M was slope. X2 and Y2 were an ordered pair, and X1 and Y1 was another ordered pair. And when we're trying to find the average rate of change, we're just trying to find the slope over a certain interval. That's going to get us the average rate of change. So when we're dealing with that, we're dealing with a function, and it asks us to find the average rate of change for f of x over the interval 1, 3. Okay. What letter this is? F. Here's our function. 2x squared minus 5x. What values are 1 and 3 in this interval? What kind? Intervals are, when we talked about intervals, we used intervals to do our intervals of increase, decrease. What kind of values did we use in those? What kind of values did we do when we were looking for the domain? We're using x values. Anytime they give you an interval and they're asking about an average rate of change, then they're talking, those are x values. Okay, these are x values always. Anytime they give you an interval, those are x values. Okay, so what we've got to do is we've got to find the ordered pair that goes with that so that we can find the slope. So we need to find f of 1 and we need to find f of 3. We got to get those y values that go with those x values. If we get those, then we've got everything that we need to find the slope. So 2x or 2x squared would be 2 times 1 squared minus 5 times 1. So we're doing function value there, going back to section 1 and using some of that stuff. So 2 times 1 squared, 1 squared is 1. 1 times 2 is 2. So that'd be 2 minus 5, which is negative 3. So we get this ordered pair 1, negative 3. And then we're going to do the same thing, but we're going to plug a 3 in. So 2 parentheses 3 squared minus 5 times 3. So I'll work that one out. So it's going to be 2 times 9, which is 18, minus 15. That's positive 3. So we get this ordered pair 3, 3. Now, the average rate of change is get the slope between those two. Y2 minus Y1 over X2 minus X1. Ordered pairs, this is X1, Y1. This is X2, Y2. That's what those are. So 3 minus negative 3 over 3 minus 1. Just do that math. 3 minus negative 3, that's a double negative, so it turns to positive. So it's going to be 6. 3 minus 1 is 2. 6 over 2 reduces to be 3. 3 is your average rate of change. Okay. Once you find the average rate of change, what that tells you is that over the interval from 1 to 3, the slope of a line is 3 across that interval. Okay, that's the average slope across that. So what you can then do with that is create what's called a secant. Write that out a little bit clearer. Secant line in slope-intercept form. This is a line that intersects a graph of a function at 2 points. That's what we're finding when we find a secant line. In geometry class, you talked about secant lines and tangent lines. We did a lot more stuff with tangent lines than we did secant lines if you took a high school geometry class. Secant lines are lines that hit something twice. Tangent lines are lines that hit something once, right? So, and there's a little bit more special stuff about tangent lines. We're talking about secant lines. When you get into calculus, you talk about tangent lines a little bit more. So secant lines are what we're after here. So what we've gotten so far is we want to write a secant line for the example we just did. Okay, we've got a function f of x is equal to 2x squared minus 5x. We've got that function there, and we want to write the secant line over the interval, and we've used 1, 3 as the interval. Okay, so write the equation for a secant line. All right, so steps to writing the equation of a secant line are, first, find the slope. That's the number one thing you do. We've already done the work to do that. We did f of 1 is 3, and f of 3 is, what was that? Or f of 1 was negative 3, f of 3 was 3. We did that in example F. We found the points, we found the slope. We took 3 minus negative 3 over 3 minus 1 and got 6 over 2, which is 3. We found the slope is 3. The second thing to do is take y equals mx plus b and plug in what you know. What do I know? I know the slope. I know M, it's 3. I also know X and Y. I've got 2 ordered pairs up here that I found when I did all that work with that interval. I've got either 1, -3 or 3, 3. I'm going to plug in 3, 3. It doesn't matter which one of the ordered pairs you plug in. I'm just going to plug in an X value of 3 and a Y value of 3 because that's this ordered pair. So that'd be 3, 3, 3. And we don't know what B is. That's what we're trying to find. Trying to find the Y-intercept for that equation. Okay, I worked that out. That's going to be 9 plus B is equal to 3. I solved that equation by subtracting 9. I get -6 is equal to B. So the third and final step is write the equation. Y equals 3x minus 6. I want to show you what that looks like graphically. If I take that original problem and I graph that, 2x squared minus 5x, and then I graph the, on y2, I graph the 3x minus 6. How many times is that red line hitting the blue line? Twice. So what a secant line is supposed to do. Okay. So what I'm doing is I'm finding an equation of a line that hits the graph of the original function twice and using the interval that they tell me to work through. Okay. Let's do another one of those problems with a different function so we get the full way of doing this here. So I think it's example H maybe. Yeah. F of x. 3x squared minus 2x plus 3 over -2 to 1. Write the equation of a secant line. Right? Write the equation of the secant line. All right. So we got the interval. Remember, these are x values. Those are x's. So we need y's to go with them. How do we get y's to go with x's? We do function value. Figure out what f of -2 is. I'm going to use the calculator to help me out here. Get that view off of there. It bugs me. All right, so we got 3 parentheses -2 squared minus 2 parentheses -2 plus 3. So I'm just plugging in what I'm working out right here. Hit enter. Positive 19. All right, so f of -2 is equal to 19. And then I'm going to work out f of positive 1. May not need a calculator for that. 3 minus 2 plus 3. So that'd be 6 minus 2 is 4. So I have another ordered pair. F of 1 is equal to 4. I've got the ordered pairs. The next thing I need to write a secant line is the slope. Y2 minus Y1, X2 minus X1. Doesn't matter what order you start with the Y values as long as you keep the X values in the same order. So I'm going to start with 19 minus 4, and that means I have to do -2 minus 1 on the bottom. So it'd be 15 over -3, which is -5. That's the slope of the line. One, ordered pairs. 2, slope 3 is the equation. Okay. So the equation starts out with y equals mx plus b. That's the way it should start out. We know the slope is -5, so that's what we're going to put in here. We've got two ordered pairs to choose from to put x and y in there. It doesn't matter which ones. I'm going to pick the smallest ones, 1 and 4. Okay, 4 is y, x is 1. You would get the exact same answer if you used -2 and 19. It doesn't matter which ones of those you use. Just pick one of the ordered pairs, whichever one you think is the easiest. Okay? Work this out. Get b. That's going to be -5 plus b, 4. I would add 5. That works out nice. B is equal to 9. So the equation is y equals -5x plus 9. That is our secant line. That's what we're looking for. Secant line is what we're looking for. Takes a little bit of practice, but if you'll follow that, kind of step by step, what I'm showing there in order that you're going to do things, that will help you out as far as knowing that and knowing that order and working your way toward understanding that. Page 237, I believe, in section 3.3, 1 through 79. Odd, obviously, out of that. And that gets you the sections there.